Right.
Okay, so welcome everybody. And today is Quantum Day. And for this reason, we decided to have a quantum information related talk. And we are very happy to have Alison Warman telling us about categorical symmetries from phases to phase gates. Take it away.
Thank you very much for the invitation to speak at this very nice seminar series. This talk will span from mathematics to condensed matter and quantum information. As Andrea reminded us, today is World Quantum Day, at least according to Google. So since we're at the Symmetry seminar, let's start with symmetries. So starting with this paper by Gajotica, Pustin, Seiberg, and Willett, the notion of symmetry in quantum field theory has substantially expanded to include any topological operator. These in particular can act on extended defects and fuse non-invertibly. Mathematically, they're described by higher fusion categories, and physically give rise to a wide landscape of different theories and phases. A powerful tool for their study is the symmetry topological field theory, because if we view the theory as living on the physical boundary, the SymTFT enables us to encode its symmetry-related properties in a d+1 dimensional topological bulk with a topological symmetry boundary. So in the first part of the talk, I will review the SymTFT construction and how it enables us to systematically classify quantum phases, both gapped and gapless, and in particular, how these gapped boundary conditions and interfaces will be used, for example, to generate new phase transitions with non-invertible symmetries. In the second part, so then I will also comment on how the SymTFT ideas can also be extended to study symmetries of mixed quantum states described by a density matrix rho. And in the second part of the talk, I will then show how very closely related ideas of topological field theories with boundaries, so here we see a 2+1 V bulk with free boundary conditions, can be used to encode logical quantum information. So we can think of this anion configuration as a quantum state psi, and then symmetry, an automorphism of this TQFT, will be used to construct unitary gates acting on the quantum state, if we think of this as moving parts. So the main message of this talk will be that the same mathematical ideas of topological field theories that with boundaries and interfaces can not only be used to systematically classify quantum phases of matter, but also to construct phase gates of arbitrary precision purely in 2D, which can provide a route towards universal quantum computation. Although generalized symmetries can in general be complicated, the technical tools I will use in this talk are only those for finite group TQFTs. So if we take G to be a finite group, we can consider its quantum double, whose representations are topological lines in a 2+1 TQFT. This is known as a digraph-Witten theory, and one can very explicitly compute all its modular data. Now, the topological line defects are anions labeled by a conjugacy class, G, and an irreducible representation of the centralizer. And they can be anions because the spin of this topological line is given by basically the character of G in the irrep R. Okay? If we take the simplest example, Z2, then the electric anion is a boson. They carry in the non-trivial irrep, while the magnetic anion is also a boson, which carries the non-trivial group element. The reason they're called electric and magnetic is that if we think of this as a G-gauge theory, then E, carrying the non-trivial representation, is like a Wilson line, whereas M is like a Toff line, whose holonomy is indeed this group element G. Before we discuss the details of the classification of phases from the SymTFT, which we've already heard about in certain talks in this series, I would like to point ahead towards the quantum computing applications. So the key idea behind topological quantum computing is to encode quantum information in global topological degrees of freedom. For example, anyons wrapping the non-contractible cycles on a torus or stretching between gapped boundaries. And these ideas date back to Kitaev and his toric code. Since this quantum information is encoded in global topological degrees of freedom, it is inherently robust to local noise and errors. And this is why these topological codes have attracted considerable interest from the quantum information community because of their properties of potential fault tolerance. The results I will discuss are that we can construct arbitrary precision gates purely in 2D. This is surprising because if one considers codes based only on the abelian group Z2, with Hamiltonians comprising only of Pauli operators, then the only unitaries that can be implemented are those that map Paulis to Paulis. And these are not universal, as I will explain. Instead, using non-abelian groups, we can obtain arbitrary precision purely in 2D. Now, before we come to this, let's start the first part of the talk on topological interfaces for quantum phases. Using the SymTFT, we can systematically classify gapped and gapless phases with generalized symmetries and compute in detail the ground state degeneracy, their local and string order parameters, and the deformations between them. Then, using lattice models, the SymTFT predictions can also be verified. And I will also explain how the SymTFT has recently been extended to describe mixed quantum states. Now, an important tool, both for the symmetry properties of phases and for the quantum information applications, is that of gapped boundary conditions. As I said, for this talk, we will focus on TQFTs for finite group G. And in this case, the boundary conditions are simply labeled by a subgroup, K, and a 1 plus 1D SPT. So remember that the bulk here is in 2 plus 1D. So the boundary is labeled by a subgroup and a 1 plus 1D SPT. So physically, we can think of this as starting with the gapped boundary condition for G symmetry, also known as the Dirichlet boundary condition, on which all the irreps can end, all the charges, and then stacking with the 1 plus 1D SPT here on the boundary, and then gauging the subgroup K. So this will give rise to a maximal condensable algebra of anyons that can end on this boundary. The anyons instead that get projected and remain non-trivial will generate a possibly non-invertible symmetry S. So from the symmetry point of view, the gapped boundary conditions are useful for generating different symmetries. And we will see for classifying gapped phases. While from the quantum information point of view, they're very useful because if we consider a setup with two boundaries, we can then have inequivalent quantum states that differ by anyons stretching between the two boundaries. Another important tool is that of interfaces between topological orders. So these are, if we start with, for example, D of G, and then we want to go to a smaller topological order, this can be obtained by condensable algebras, which are classified by the following data. So if we think of this as having G symmetry, then H is a subgroup which corresponds to the preserved symmetry. N is a normal subgroup, which is the symmetry that acts trivially. And that's why the reduced TO is this quantum double for H mod N, which is a group since N is normal. And then there's also some SPT data and the edge charges of the SPT. Interestingly, so this is the full algebra data, and then it can be mapped to anyons, but there can be cases where inequivalent algebras are defined on the same anyons. And these can have interesting physical consequences for gapped phases and for phase transitions, as will appear shortly. So from the symmetry point of view, these type of interfaces are very useful because they enable us to start with some larger, more complicated symmetry, and then go to a reduced TO for a smaller, simpler symmetry. From the quantum info perspective, again, they are useful because we may need to use a complicated code to implement high precision gates. But then these kind of interfaces will allow us to switch to simpler Z2 codes. Now, these are some of the many papers which have worked on the SymTFT for gapped phases and for gapless phases. So the bulk is topological, and so is the symmetry boundary. If the physical boundary is also topological, then after compactifying the SymTFT interval, we will obtain a gapped phase whose ground state degeneracy, for example, is given by the number of anyons that can end on both the symmetry boundary and the physical boundary. And then the symmetry properties on these vacua follow from the Lincoln action of anyons in the bulk. Instead, using these non-maximal algebras, we can construct second-order phase transitions for a larger, more complicated, possibly non-invertible symmetry, starting with phase transitions for smaller, simpler symmetries. This is achieved as follows. So suppose we start with some larger, complicated symmetry S, and then we have an interface to a smaller topological order, like B of K. For example, we can take K, there are cases in which K is Z2. Then we can input here a conformal field theory for this smaller symmetry, for example, easing. This is a CFT between, for example, two K-symmetric gapped phases described by these Lagrangian algebras L1 and L2. So in the concrete cases, when K is Z2, we can input here the easing transition between the Z2 trivial and the Z2 SSB phases. Then, using the map of anyons determined from this interface, we can map this CFT as a transition between two K-symmetric gap theories to a CFT with the full S symmetry as a phase transition between two S-symmetric gap theories. So we can use this club sandwich technology to produce new phase transitions from known simpler ones. An explicit example of this is for rep D8 symmetry, where only on this slide D8 has order 8. And rep D8 has a Z2-Z2 invertible symmetry given by 1D irreps, which are shown here in red and green, which act invertibly, and a non-invertible two-dimensional irrep, which is shown here in blue. Now, if we consider two gapped phases, one which is labeled by this normal subgroup N, which is a Z2-Z2, with this rep D8 symmetry action, and another gapped phase labeled by the full D8 subgroup, we can then use that club sandwich technology to construct a gapless transition between. Now, first I want to add a comment about this rep D8 SSB phase. So we see that this has 5 vacua, which correspond to the 5 simple objects of rep D8. There are 4 vacua here, 1, 2, 3, and 4, which are obtained by applying the 1D irreps, the invertible symmetries. And by constructing an explicit lattice model, we can verify that these 4 vacua are just tensor products, okay? And we can obtain them with the invertible symmetries. However, this phase also has a 5th ground state, which is obtained by acting on either of these with the non-invertible symmetry, as we see here. And whereas the first 4 are just tensor product states, the 5th one is entangled. So interestingly here, we need non-invertible symmetry to explain ground state degeneracy, and we have a ground state manifold with different entanglement properties. Now, the phase transition between these two gapped phases can be obtained by taking this condensable algebra. So here it's labeled by data, which comes from these subgroups labeling the 2 phases. So here we take H to be the 8, which is this one. And it means that this algebra is a subalgebra of the one for this gapped phase. Okay? And then we take N to be this Z2, Z2. So it means that this can be deformed to, that the theory corresponding to this algebra can be deformed to these 2 gapped phases. Now here, if we take the quotient, then the reductio is Z2. So we can precisely input the easing transition and then use the map of generalized charges to map it into a CFT on which the full rep D8 symmetry is realized as follows. So we see that this is a CFT with 3 easing universes related by the rep D8 symmetry. So one of these universes, Ising 0, is invariant under the full Z2, symmetry, whereas Ising plus and Ising minus are exchanged by an invertible Z2. And the non-invertible symmetry acts as follows. It acts like the Kramers-Wanier duality between the Z2 trivial and the Z2 SSB. We call this an intrinsically gapless SSB phase because it's a gapless spontaneous symmetry breaking phase because we have multiple universes. But it's intrinsically gapless because this symmetry breaking pattern is not exhibited by the gapped phases. So this is a CFT between these two gapped phases, which have a greater number of vacua. So the degree of symmetry breaking here increases. Anyway, so the main message here is that using this technology, we can input a very simple transition Ising and then obtain phase transitions for these non-invertible symmetries. Now, all of this was for pure states. However, in realistic situations, one has to contend with noise and decoherence, in which case the quantum states are describing are actually averages of pure states described by a density matrix. Now, if all the pure states appearing in this average carry the same symmetry eigenvalues, then the density matrix rho is said to have strong symmetry. Indeed, we can clearly see that if it's an average of states that are all eigenstates of the symmetry operator D with eigenvalue C, then so will rho be. However, more generally, if rho is an average of states which have different symmetry properties, the density matrix can still have a weak symmetry, acting as follows by conjugation. This can happen, for example, if rho is an average of Z2 even and odd states. If we act by conjugation, the two minus signs and the Z2 odd sector will cancel and we will still get rho back. Okay. Now, how can we use the SymTFT to describe the symmetries of these mixed states? The answer is to map the density matrix into a pure state in a doubled Hilbert space and interpret the strong symmetries, which are here acting, for example, on the left of rho, as a symmetry acting only on one copy of the Hilbert space. So strong symmetries can act on the density matrix independently from the left or independently from the right. And in this pure state picture in a double Hilbert space, it means that they act independently either on the left Hilbert space or on the right Hilbert space. Weak symmetries instead, which act on the density matrix by conjugation, get translated in this setting to operators that act diagonally on the tensor product Hilbert space. And interestingly, there are fusion constraints coming from these weak symmetries. Because if we have all weak symmetries, then the fusions must be invertible. This is because if we consider some non-invertible weak symmetry, so if we act on the density matrix rho, first with the weak symmetry B and then with the weak symmetry A, and if we now use the fusion properties of these symmetry operators, we will then get a sum of their fusion outcomes in the non-invertible case. And these will now act independently on the left and the right of rho. They won't, since here we have a sum, this will not act in general by conjugation. So this is why the fusions of weak symmetries must be strong symmetries. Now there's a nice interface way to derive this from the SymTFT. If we start with the SymTFT for a strong symmetry, which means that we have operators acting both on the left and right, so we can think of this as the SymTFT for S left and S right. And then we consider a condensable algebra of diagonal charges. This will break part of the strong symmetry to a weak symmetry. And interestingly, the mathematics of condensable algebras gives us all these constraints on possible symmetry breaking patterns from strong to weak. In particular, while for invertible symmetries, if we start with G times G, then a diagonal G symmetry always exists, which means that we can always make an invertible group symmetry weak. This is not the case for non-invertible symmetries, confirming these constraints that we see also from diffusion rules. However, we can see from this technology that there are cases in which you can make, for example, a non-invertible symmetry weak while keeping its fusion outcome strong. For example, if we start with Ising times Ising. So the main message here is that the SymTFT as a topological field theory with its boundaries and interfaces gives a very powerful method to systematically classify gapped and gapless spaces, to produce new gapless spaces from known simpler ones, and to also contain the symmetries of mixed states. Are there any questions on this first half of the talk? Can you hear me?
Yeah, I can hear you.
Okay. Good. Then if there are no questions, I can move on to the second part, where we will show how these same mathematical techniques of topological field theories with their boundaries and interfaces can be used to naturally construct topologically protected quantum computing gates of arbitrary precision purely in 2D. So let's remind ourselves of the idea behind topological quantum computation. So the idea is to encode quantum states in global topological degrees of freedom. For example, the anyons wrapping the non-trivial cycles on a torus all stretched between boundary conditions on a plane. And the reason it's useful to consider to encode information in these global degrees of freedom, which are topological, means that they are inherently robust against local noise or errors. Indeed, if we think this is topological, it means we can deform it without altering the information stored here. This means that it's a promising candidate for fault-tolerant quantum computing. This is the notation, standard notation I'm using for the qubits and for the Pauli group. And importantly, we can represent the qubit states on this block sphere, where 0 and 1 are the north and south. These are the plus and minus 1 Pauli Z eigenstates. Then we have the Pauli X eigenstates at the front and bottom, and Pauli 1. So why should we care about quantum computing? The reason is that quantum computers can provide an exponential speedup compared to their classical counterparts for certain algorithms. So an example is Simon's algorithm, where if one considers a function here on n bits, okay, with period c, okay, so this is a function which has a certain periodicity, then if one wants to determine the period c classically, one needs to basically check an exponential number of states, because as we know, in this this Hilbert space, we have like 2 to the n states. Instead, so one needs to basically scan, if one does it randomly, an order 2 to the n over 2 states. However, quantum mechanically, we can use quantum interference between f of x and f of x plus c to constrain the period c with n linear equations. So the complexity of this goes from exponential to linear. This same idea of periodicity finding is behind Shor's algorithm for factoring primes, because there's a mathematical connection between finding periods and prime factorization. So quantum algorithms can have an exponential advantage over classical ones. Now, we've seen here the block sphere of states of qubit. Now, how can we describe the unitary operators acting on these qubit states? So these can be organized into levels of the so-called Clifford hierarchy, where level 1 is defined as the Pauli group, okay, the Pauli X, Y, and Z generators. Then level 2 is defined as the set of the group of unitaries that conjugate Paulis into Paulis. Okay? However, these Clifford gates can be easily simulated classically. And this is precisely because they map Pauli to Paulis, we can keep track of their action classically just using order 2n bits. And the reason is that basically the Pauli group can also be generated by x, z, and the phase I. So we can encode these Pauli states just in terms of classical bits, labeling basically X and Z. So we need 2n classical bits. And since the Clifford gates map Paulis to Paulis, one can keep track of the action also on a classical computer in polynomial time. Furthermore, precisely because they map Paulis to Paulis, it means that we can only explore these 6 points of the block sphere of the Pauli eigenstates. If we start with a Pauli eigenstate and we conjugate by Clifford gates, we can then get mapped within just 6 points on the block sphere, and we can't approximate arbitrary states, arbitrary unitaries. That's why we need to go beyond the Clifford group. We need to go to non-Clifford gates to obtain genuine quantum advantage. Now, Clifford levels K are defined recursively as the set of unitaries that conjugate Paulis into level K minus 1. And we see that this definition is consistent with defining level 2 as the set of unitaries that conjugate Paulis into level 1. Okay? This is the generalization. And we see that they contain these phase gates here. Again, this is consistent. If we set K equals to 1, then we get the Pauli Z. If we set K equals to 2, we get this S gate. If we set K equal to 3, we get the so-called T gate, and so on. There are also unitaries that fall outside of this hierarchy. For example, if they have like phases with factors that are not powers of 2. Now, an important theorem by Bravi and Koenig is that if one considers a topological code in low spatial dimensions and with a local nearest neighbor Hamiltonian comprised of Pauli operators, then the topologically protected gates at level K of the hierarchy can only be implemented in K space dimensions. Okay? So if we're only in 2 dimensions, one can only implement Clifford gates, which are not universal and can easily be simulated classically. So I also want to comment that in these topological codes, one has usually a large number of physical qubits on the lattice, whereas the qubits that the states that are used for the actual computation are called logical qubits and denoted with a bar, and correspond to these states that differ by global topological degrees of freedom. So Bravi and Koenig showed that the logical operations on the logical qubits using Pauli operators are constrained to level K of the Clifford hierarchy in K space dimensions. So in 2D, only Clifford gates which are not universal. So how can we go beyond this? We still want to consider a low spatial dimension, ideally 2 dimensions. And we want to maintain the nice properties of having a local nearest neighbor Hamiltonian. However, we will abandon the requirement of Pauli operators in the Hamiltonian, which in the quantum information context is also called stabilizers. The answer then is to use quantum doubles for these finite non-abelian groups G. The result is that we will be able to construct topologically protected phase gates of arbitrary precision purely in 2D. There are also related constructions used in lattice surgery or constructing just the T gate. Now, how do we do this? So the key idea is to first encode logical information in these global topological degrees of freedom. So to achieve this, we'll define the trivial logical state as just an empty patch with no anyons, and the non-trivial logical state as being obtained by a trivalent junction of anyons ending on these boundaries. So here, this triangle is the spatial cross-section of our 2+1 DTQFT with 3 boundaries. And these boundary conditions are such that A1 is can come out of L1, A2 for L2, and A3 into L3. So this is a non-trivial global degree of freedom given by this trivalent anion junction, and it's therefore a topologically inequivalent state compared to the trivial one. But why is this a qubit state? So what's the requirement for this to be, why can we interpret this as a qubit? So in addition to this trivalent A junction, there also needs to be a junction of anions labeled, which we can call B, such that the triplet of A anions and the triplet of B ones have a -1 braid-in. So from the TQFT perspective, the -1 braid-in will then get translated in the quantum information perspective as the anti-commutation relation between the logical X and the logical Z operators. So we take our 2+1D TQFT on a 2D spatial patch, triangular patch with boundaries. We choose the boundaries such that there is this trivalent anion configuration that is clearly, this is inequivalent to the trivial one, and such that it has a -1 braid-in with another trivalent junction, such that it will correspond in quantum info to the -1 commutation relation between Pauli X and Pauli Z. So now that we have our logical states, we want to perform computation on them. So to do this, we want to use symmetries. Now, the symmetries of this 2+1D TQFT are classified by invertible interfaces. Here we want to consider automorphisms, so invertible interfaces that map each anion of the NG uniquely to another anion. Now, a class of such interfaces, inspired by condensed matter perspective, are those obtained by stacking basically an SPT on this surface. So here actually we consider a group 2 co-cycle, so we should think of this really as a 1+1D SPT, but we can stack it on this like 2D surface. Since this is a setup with boundaries, this 2 co-cycle also needs to trivialize on the boundary. So said another way, there need to exist boundary counterterms. And this is because basically this surface is like an anomaly for the 1D line. So it needs to be cancelled by boundary counterterms. Okay. So the message here is that automorphism symmetries of these TQFTs with boundaries are classified by 2 co-cycles with boundary counterterms. And we will use these to implement logical operations on our qubit states. Now, putting everything together, we see here in this picture that we have our state, a state, which can be either trivial or this non-trivial state with the 3 anions. So this is a logical state, which you can denote by psi. Then we use an automorphism symmetry of the TQFT to construct a unitary U, which is obtained by evaluating this group 2 co-cycle in the bulk. This is like stacking this one plus this like SPT on this surface bulk with the boundary counterterms beta. These are instead functions only of one group element. Now, if we start with the completely trivial state, then the unitary will act trivially. Whereas if we start with a non-trivial state, for example, where these anions correspond to group elements, to conjugacy classes labeled by group elements G1 and G2, we then need to evaluate this 2 co-cycle alpha on G1, G2, and then stack by the boundary counterterms. So beta 1 here for G1, beta 2 for G2, and beta 3 for their product here. Okay, so beta 3 here is because there's some difference orientation. So the key message is that we encode logical information in these global topological degrees of freedom using anions that can form these trivalent junctions thanks to the boundary conditions. And then we implement an operation on this logical state by stacking with an SPT, with an automorphism symmetry with its boundary counterterms. There's also a very concrete lattice realization for all of this, which already appeared in Kitaya's paper. This is a generalization of the toric code, vertex and plaquette operators. So for the toric code, there's a vertex operator which has Pauli X, 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 X. Its generalization to finite groups is to have left and right multiplication operators, okay, defined as follows. So here, if it goes into the vertex, we have right multiplication. If it comes out, left multiplication. And then there are plaquette terms, which in the toric code can be written as like 1 plus z, 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 z. In the non-abelian case, they one basically takes the product of group elements according with orientation, so G1, G2, G3 inverse, G4 inverse, and projects onto flux G. Then the Hamiltonian implements gauging of the symmetry. So we basically take, it's the disordered sum over these like vertex terms for all group elements. And it projects on, so this projects onto zero charge, whereas the BPA term projects onto zero flux, onto trivial flux. That's why it's labeled by the identity. And furthermore, importantly, with boundaries, we also need to include these boundary terms, and these are just basically truncated at the boundary. So I just want to say that everything can be also made very explicit on the letters. And similarly, the unitary gate that we construct can also be evaluated very explicitly, where the boundary counter terms are simply evaluated on the edges, because here each edge is labeled by group elements. So we can evaluate the boundary counter terms simply on these boundary edges, whereas the bulk SPT is evaluated on these plaquettes that we need to triangulate. Okay? So the unitary can also be written in this very concrete lattice realization. So we've seen that there's this general construction. We can provide this general construction for finite non-abelian groups. Now, if we want to go beyond Clifford gates, we need a non-abelian group. Otherwise, Baravi and Koenig showed that if we just use Z2, we can only obtain Clifford gates, which are not universal. So we want a non-abelian group, and we want to encode a logical qubit. This means that we need a -1 link-in, -1 braid-in between some electric and magnetic triangles. Then we want to implement a unitary gate from this SPT second. So we need non-trivial second cohomology for this group. And luckily for us, dihedral groups have all these properties. And we can use them to construct these phase gates at arbitrary precision purely in 2D. And it's actually even better because the dihedral groups also admit very natural code switching to Z2 based codes. These use interfaces very similar to the ones we've seen for the phasors. And if the order of the dihedral group is a power of 2, we can also implement all of this just in terms of qubits, of physical qubits on the lattice. Now, let's see how the logical states are concretely implemented for dihedral groups. So here we use a convention where the dihedral group is labeled by the rotation subgroup. So there's a Z4n rotation subgroup.
These are just,
yeah.
Could you also use Heisenberg groups?
Sorry?
Could you also use Heisenberg groups instead of dihedral groups?
Probably yes. I'm not sure right now of the details. Like the point is that we need boundary conditions such that we have a logical qubit, where in this case, for the dihedral group, we take the group elements Rs, where S is the rotation and S is the reflection, S and R. And this can be seen, this is a logical qubit because there's a -1 link-in with the triangle of irreps. Because the dihedral groups have these 1D irreps with character -1, there's -1 braid-in phase between these kind of magnetic anyons and the electric anyons for the 1D irreps. So this is why we can have a logical qubit. Then we also need the non-trivial second group homology for the unitary to construct the logical action. And it's also, as I said, very useful for applications to be able to switch to Z2 codes, which is also, we can also achieve for the dihedral groups. I'm not sure now of the details of like if the Heisenberg groups also satisfy these properties.
I see.
We can.
So for larger n, you get better precisions?
Yes,
right?
Exactly. Yes.
I see. Thank you.
So this is how we encode the logical states. While this is how we construct the unitary. Now we need to take a non-trivial 2-code cycle, which mathematically can be computed using the central extension. And it takes these values on the states of interest. So here we consider this trivial state with all identity group elements, and this non-trivial state of these magnetic anyons labeled by these group elements representing conjugacy classes. So for us, basically, this 2k cycle is trivial both on the identity and on RS and S. When we restrict it to the first boundary here, there's a boundary labeled by the RS subgroup and by S subgroup, and on both these boundaries, alpha is just identically 1. Whereas if we restrict it on the boundary labeled by the rotation subgroup, it's not identically 1. It's written as delta beta, where beta is like evaluated on R is this following phase. So now, if we remember the formula for the unitary, this is obtained by stacking this like 2k cycle with the boundary counter terms. And we see that in this case, everything's very simple. So there's no contribution from alpha, there's no contribution from beta 1 or from beta 2, because alpha just identically 1. Whereas we have a contribution here from beta of R. And these are exactly the phases for this T to the 1 over n gate. And as Andrea rightly pointed out, if we increase n, we get better precision. And we can get arbitrary precision purely in 2D, purely in a topological setting, using these nearest neighbor Hamiltonians just by increasing the order of these dihedral groups. Interestingly, we can also map the Hilbert space to one spanned by qubits. And this basically uses a property known as supersolvability of the groups. So basically, here we have Zn, Z4n rotations. Now, when the order of this group is a power of 2, we can basically map the states here written as group elements, R to the A, S to the J, to states labeled by qubits, where we take the binary representation of A, and then we just take the value 0 or 1 of J. Okay, so for example, if we consider here like D4 with Z4, like if we take 0, this will be mapped to like 0, 0. If we take 1 to 0, 1. If we take 2, this will go to 1, 0. And if we take 3, it will go to 1, 1. Okay, so we just take the binary representation of number A and then J. So this is a way to map the Hilbert space here, the group elements to one of n qubits. And we see here that the number little n of qubits is the same level of the logical gate in the Clifford hierarchy. And remember, from Bravey-Koenig, if one is in 2D using only, according to Bravey-Koenig, for Pauli stabilizer codes, so just using Z2, if we want to reach level n of the hierarchy, we need to go to n spatial dimensions. So for example, if we wanted level 5, we would need 5 spatial dimensions. Whereas using these dihedral groups, we can reach an arbitrary level just by increasing the number of qubits on each edge of the lattice, but remaining purely 2D and keeping the nearest neighbor Hamiltonian. So this map to the qubit Hilbert space can also be made very explicit for all the logical operators. So here we have like the left and right multiplication and the IRAP operators, and then we can map them concretely to qubits. So importantly, we can also consider interfaces that will enable us to switch from these non-abelian codes used here in the bulk that we need for these high precision gates into Z2 codes. Now, how can we do this? So remember that condensable algebras are like labeled by these subgroups, and then here we take trivial co-cycle data. And we can consider a condensable algebra where we're basically trivializing the subgroup generated by R squared, so this Z2n subgroup. So this means that we can go to Z2 as follows. Like the M1 anion of Z2 is identified with R, the M2 anion with S, and M1 and 2 with R times S. Okay, this is because we're basically making R squared trivial. So we're only left with RS and RS with this map of anions through the interface. This means that we can start with a Z2 here, this is a Z2 patch that encodes the one logical qubit with this triangle. And we can start with a plus state, which is 0 and 1. Then we use this interface to go into the non-abelian patch. We apply the unitary constructed with the two-case cycle, the SPT alpha with its boundary counter terms beta. We obtain the logical action of this, and then we use the interface to go back to the Z2 patch. So the result is that we start with a standard plus state, so 0 plus 1, and then this unitary gate will return the 0 state, but it will return the 1 state with this phase. And in the quantum info terminology, this is called a magic state, which can be used for this, for quantum computation purposes. So, in summary, we have seen that the SymTFT, with its topological bulk and boundaries and interfaces, can be used to systematically classify gapped and gapless phases and to construct new gapless CFTs with non-invertible symmetries starting from simpler known ones. The SymTFT can also be extended to mixed state phases and gives constraints on symmetry break-in properties, also in the case of states described by these density matrices. In the second part, we saw how these same mathematical ideas of TQFTs, their boundaries and interfaces, can be interpreted as non-abelian surface codes, where the qubit logical states correspond to non-trivial, trivial or non-trivial configurations of anyons stretching between boundaries. And unitary gates can be implemented on these quantum states by stacking group 2 co-cycles, so like an SPT, on spatial slices with boundary counter terms. So the same ideas here can be used with very different physical consequences. And from the quantum information perspective, this can be used to generate arbitrary precision phase gates purely in 2D with local Hamiltonians, and which also allow switching to Z2 base codes and qubit realizations in certain case when basically the order of the group is a power of 2. So in conclusion, we've seen how the same, like the mathematical ideas of these TQFTs, their boundaries and their interfaces, can have a wide variety of physical implications, from pure state phases to mixed state phases to quantum information, going from phases to phase gates. Okay, thank you very much.
Thank you for this very nice talk. So, are there questions? Maybe I can ask one. So you said that you get extra precision by increasing n, but is there some like more technical difficulties by increasing n in the sense? So is it easier to realize a lower value of n in practice than the higher value of n, or is it just something?
Yeah, so here n is the number of physical qubits on each edge of the lattice. Yeah. So clearly, if we increase n, this requires increase in the total number of qubits. And it also requires basically greater precision in the Hamiltonian, because the Hamiltonian has to act on all these n qubits. So we actually need, like, we think of all these n qubits on the same lattice edge, but clearly the Hamiltonian will need to be able to connect to all these n qubits. So microscopically, it increases the connectivity of the Hamiltonian. And also in terms of the actual gates that we need here, if we increase n, we also need higher precision phase gates even on the physical qubits. We can get a higher precision phase gate on the logical qubit, but we also need to increase the gates that we're applying on the actual lattice on the physical qubits. So increase in n requires a greater number of qubits, a greater degree of connectivity to the Hamiltonian, and greater precision. However, it's obviously, I think it's easier to increase the number of qubits than to go into like 5 space dimensions.
I see. But so do you think that there is some ideal value of n for practical
Yeah,
applications?
yeah, because if one has the Clifford operators and even one non-Clifford, it's possible to approximate arbitrary unitaries. So although it is useful for certain applications to have these gates realized exactly, they can be approximated even just by using one like the T gate in addition to the Clifford operators. So we definitely need n equals 3 if we want universal computation. So we need to be able to implement the T gate. Based on the application, it's probably useful to also have 4 or 5. So for example, one application in which these phase gates appear, these T diag with these phase gates, is the so-called quantum Fourier transform. So yeah, let me just go here. Basically, if we have the group here, okay, Z4n, we can think of it as like in the basis of group elements, but then the quantum Fourier transform basically changes basis from the group elements to the irreps. And the irreps of Z, okay, in this case Z8n, will have these phases. And this is the so-called quantum Fourier transform, basically from group element basis to irrep basis, which uses all these phase gates. And the quantum Fourier transform is used in, for example, in Shor's algorithm and in many quantum computing algorithms. So probably if one wants those certain algorithms that require these phase gates, then it's useful to have a larger number of n. Whereas if one is interested in protocols that require maybe only the T gate, then one can just restrict to n equals 3. Yeah, probably an optimal, I mean, I think the optimal value depends on the particular application one is interested in.
So it would be probably useful to have several different values of n simultaneously.
Okay, so yeah, this is important. Now, basically, if we can obtain, so all these gates basically square to each other. So if I can have t to the 1 over n, then if I take it square, I get the higher value, okay? So I don't need to have all these n's simultaneously.
Sure, but you can
I
have
can,
n that are mutually.
yeah, we need to pick the largest n we need, and then we can construct the other gates just by focusing on the, like, basically on the lower precision qubit states.
Oh,
So
okay, because
basically,
big
yeah,
n to be a power of 2. Okay, I see.
exactly, yeah, yeah. If we take n to be a power of 2, for example, if we have n equals 3, then we will have like the low, like,
I see, I
you know,
see.
the unit here. But then we can also have, you know, then if we just want the Clifford, like we then focus on like the decimal thing, and we can, if we just focus on the decimal qubit position, we can use this to have, you know, like the square of that gate.
Yeah, thank you.
Yeah, so n is fixed by the maximum precision we need, but then once we have this, we can use the other qubit states for the lower precision gates. So we don't need to change the number of physical qubits. We can just not use them.
Any other question? Okay, so if not, let's thank Alison again.
Okay, thank you very much.